Okay, so now we're going to start looking at another type of probability, so additional topics in probability and counting. So in 3.1, we looked at the fundamental counting principle. With that, we have permutations. So an important application of the fundamental counting principle is to determining the number of ways that n objects could be arranged in order or in a permutation. So a permutation is simply an ordered arrangement of objects the different permutations of n distinct objects is n factorial. Okay, so the expression n factorial or n exclamation mark is read as n factorial, and it's defined as follows. So n factorial equals n times n minus 1 times n minus 2. That's going to continue until 3 times 2 times 1. So an example, we look at 6 factorial. That would be 6 times 5 times 4 times 3 times 2 times 1. All right. And we have a special case, 0 factorial simply equals 1. So an example, the objective of a 9x9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3x3 grid contains the digits 1 to 9. How many different ways can the first row of a blank 9x9 Sudoku grid be filled? So we have 9 numbers, 1 through 9. So 9 factorial. Okay, so you can do 9 times 8 all the way down, and you get 362,880 ways. I'm going to save the second example in class, and I'm going to show you how to do it in your graphing calculator. All right, so suppose you want to choose some of the objects in a group and put them in order. So instead of choosing like all 9 digits, suppose you only want to choose 7, okay? So this is called a permutation of n objects taken r at a time. And we have a formula, which I'm going to write underneath here. And so n PR, where n and r are your subscripts, equals n factorial divided by n minus r quantity factorial, where r is less than or equal to n. Okay. So if we want to find the number of ways of forming 4-digit codes in which no digit is repeated, okay? So we talked about this in 3.1 using the counting principle. Okay, we had a 4-digit code, no digit is repeated, and we did 10 times 9 times 8 times 7. Okay. So that's what we did in 3.1. Now for 3.4, using our permutations, we know our n is how many digits there are, and we know there are 10, and we're choosing 4 of them. Okay, and since our order matters because no digit is repeated, we're going to do 10 permutation r, which equals 10 factorial divided by 10 minus 4 factorial. Well, 10 minus 4 is 6. So we have 10 times 9 times 8 times 7 times 6 times 5 times 4. Move this up real quick. Times 3 times 2 times 1. All over our 6 factorial. Well, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So those all cancel. And we're just left with 10 times 9 times 8 times 7. So same thing we did when we had the fundamental counting principle. And if we plug that in our calculator, we get 5,040. Okay. And again, I'll show you another way on next class and how we can just plug that into our graphing calculator. So I'm going to save these next two examples for that. So sometimes you want to order a group of n objects in which some of the objects are the same. For instance, consider a group of letters consisting of 4 A's, 2 B's, and 1 C. And we want to know how many ways can you order such a group. Okay, so using the previous formula, you might conclude that there are 7 factorial, okay, or 7p7 possible orders. However, because some of the objects are not the same, not all of these permutations are distinguishable. So what that means, distinguishable permutations, is where n are of one type, and 2 are of a second type, and so on. Is, now our formula, so we're going to take n factorial, so how many total, divided by how many of those are duplicated. So the number of n1 factorial, n2 factorial, n3 factorial, keep going until you've listed everything. Okay, but your key here, so where n1 plus n2 plus n3, going all the way up until you've listed everything, equals your n. Okay. So if we look at this example, a building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. And how many distinguishable ways can the houses be arranged? So we have n equals 12. We add all those up. So that's our numerator, 12 factorial. And then we're going to look at our groups. Okay, we have 6 of 1, so 6 factorial. We have 4 of our next, so 4 factorial. And then lastly, we have 2, so 2 factorial. Okay, and if we check, 6 plus 4 plus 2 equals 12, so that checks out. And now you're just solving. Okay, so if you write this all out, over and then just start canceling. So our 2 and our 1 can cancel, our 3, our 4, see our 5 and 6 can cancel here. Okay, 3 times 4 is 12, so those can cancel. And then we're left with, let's see here, we have a 2 times 2, which is 4, which can cancel with our 8, and we're left with 2 up top. So we have 11 times 10 times 9 times 2 times 7, which I'm not going to try doing that in my head right now. We get 13,860 ways. Okay. And then we're going to again look at this next example next class. Okay, so now looking at combinations. So what if our order doesn't matter? So we looked at permutations, position, order matters, combinations is when it doesn't. So this is the number of combinations. Of our objects selected from a group of n objects. Without regard to order, is NCR for combination, which is n factorial divided by n minus r factorial. So the same thing we had for permutation. But then our denominator, we're also going to include r factorial. And this is again where r is less than or equal to n. Okay. So if we look at this first example, a state's Department of Transportation plans to develop a new section of interstate highway and receive 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 16 bidding companies? So because it says combinations, we know we're using C. Also because it doesn't matter which order we choose that for. We're not ranking them at all. We're just choosing 4. So we know our N is 16 and our R is 4. So if we plug this into our formula, 16 combination 4, we have 16 factorial divided by 16 minus 4 factorial and 4 factorial. So we have 16 times 15 times 14 times 13 times 12 factorial. And I'm stopping there because 16 minus 4 is 12. So these will cancel. And here, let's actually erase that 4 factorial. Let's rewrite that as 4 times 3 times 2 times 1. So let's see here. 16 and 4 can be divided, and we're left with 4. And then the 15 and the 3, and we're left with 5. And let's do 4 and 2, we're left with 2. So here we're left with 2 times 5 times 14 times 13, which equals 1,820 ways. Okay. We're going to save the second example for in class tomorrow. And then same as our application. So we're going to kind of actually wait and save the rest of these examples for class for after I show you how to use everything in our calculator, just to make things go a little simpler.